Hello, everybody. All right, let's get going. Hi, everybody. Welcome to Tuesday. So today we're going to be talking more about random variables. This lecture builds pretty naturally off number 18. So I'm going to start by talking about geometric random variables and their expectation. Last time I said without proof that the expectation of such a random variable is 1 over p. So I am going to tell you where that comes from using an idea called the tail sum formula. There's other ways you can compute the expectation of a geometric random variable in many ways, but this is a new trick. I think it's nice to see. And the basic idea is I'm going to give you a different expression for the expectation, different than the one we saw before. Oh, and by the way, if you missed it, I did record a supplementary video where I re-explain the reason why we have that expectation formula. So if you haven't watched that and you want to know, check that out. But this is an alternate formula, and this one I will explain properly because I had no barfing child all night. And so here, let me talk to you about this formula. So what we're going to do is use this formula to compute the expectation of a geometric random variable. And before I use this formula, I'm first going to justify this for you, right? So this formula turns out to be exactly the same as our normal expectation formula with one caveat, which is that this formula only works if the range of the random variable is a subset of the natural numbers. Once you have a random variable which has, for example, 0.6 in its range, this isn't going to work, obviously. So let me show you why it does work if the range is a subset of the natural numbers. So what I'm going to do here is I'm going to write out the usual formula for expectation here, and I'm going to do one little funny notational thing. To make my notation more compact, I'm going to represent the probability of x equal to I. Remember, that's just an event. What is in that event? All of the sample, actually, a question for you. The event x equals I is all the samples in the sample space that what? So an event is just a subset of the sample space. So what events go in the sample, go in the event x equals I? In a phrase, I don't know, it's subtle. It's one of those things you're still building, yeah. Yeah, where the output of x is I, exactly. So it's all the samples, you put them through x, it's a machine, a function that takes samples, and it gives you back a real value. This is all of those samples, which get mapped to I, okay? And so I'm going to represent that probability just by p sub I because it's smaller in terms of the number of square centimeters it occupies. So what I could do is write out this expectation, the normal expectation formula, as 0 times p sub 0, because that's the probability that x is equal to 0, plus 1 times the probability that x equals 1, and so forth. This is the usual formula. Then what I'm going to do is say, well, really, this is just 2 p2s and 3 p3s and 4 p4s, and then I'll just bunch them together. So there's only 1 p1. There's 2 p2s, 3 p3s, 4 p4s, and then I'm going to reorganize yet again to say, oh, well, let's take the sum of all of the p's, put them all together. And then when I form the second sum, I've already used up p1. So it's just going to be p2 through forever. The next one's going to start with what? p3, because I already used both of my p2s. So I'm using my last p3 and so forth. And if you think about what this really is, this is just the sum of the probability that x is greater than or equal to 1, the probability that x is greater than or equal to 2, and so forth. Why is this thing the probability that x is greater than or equal to 1? So I'm claiming this thing right here is the same as this. Why? Give me an argument. Yeah? Right, the probability that x is 1. The probability that x is 2. The probability that x is 3, and so forth up to infinity, which is just the probability that x is greater than or equal to 1. And there you have it. So this formula, if you just rearrange this slightly, you will get that. If you write a sigma notation, you get what's up top. Right, any questions about that? So it's just a clever argument, a different way to phrase our normal expectation formula, and it only works if we're talking about the natural numbers, because otherwise you can't do this trick where you take one of these blobs and turn them into the probability that x is greater than or equal to. Okay, so it's a handy formula. What's it good for? Well, it lets us do certain types of expectation very easily, like the geometric random variable. So question for you, there's no little picture you can, or no Google form for this one, but there's many more coming. So suppose you want to compute the expectation of a geometric random variable and you use this formula, then you need to know what is the probability that x is greater than or equal to I. We did a very similar problem in the previous lecture. So what is it? So think about this for a sec. Think about what is that probability in terms of p. Remember, p is the chance we get heads. And the question is basically, what's the probability that the first I minus 1 flips are all tails? Okay, I'm spoil that one. Okay, so the probability that the first I minus 1 flips are all tails is going to be 1 minus p to the I minus 1. So a geometric random variable has this nice property that its probability that it is greater than or equal to some value is a simple expression. That's not true for all other random variables. Like a binomial, it's not going to be so nice. Here, it is nice. Okay? So once I have this expression, then I just need to sum this for all possible i's. Okay, so plugging this into the tail sum formula, we're going to do something very similar to what we did last time when we showed that the distribution actually sums to 1. So we're basically going to say, okay, the expectation of x is this formula. For geometric random variables specifically, this probability that x is greater than or equal to I is 1 minus p to the I minus 1. So I plug all that in, and when I do that, this is just going to be my usual geometric series formula. And so I'm going to end up with 1 over 1 minus p, and so we end up with 1 over p. So that's the proof that the expectation is 1 over p. Yes?
Is that why it's called a geometric distribution?
Yeah, it sounds like a great reason it's a geometric distribution. Yeah. Is that the actual origin of the name? I actually don't know. I mean, it makes sense to me, but I've never really thought about it. What's interesting about these distributions to me is, of course, they were invented a long time ago and didn't always have the machinery of random variables. And one of the history of mathematics questions I don't really know is, how did it come to be that random variables had their precise formulation created? Like, who did it? When did it happen? I don't know. Maybe Manuel knows, but I certainly don't. It's pretty interesting to wonder, because to me it feels like, what else would you do? But I'm sure that there was an informal version of this before. So I don't know how it came to be, but my scholarship will grow over time. All right. So that's vignette number 1. This really should have maybe been in the previous lecture, but there wasn't enough time, so I put it in this one. All right. This is going to be a new big picture. So there's basically 4 big pictures today. The first is, hey, there's another way to do expectation different than before. This one's going to be a very handy idea that students get tripped up on jointly distributed random variables a lot, but they're really not very complicated. And I'm going to try and show you a couple examples to convince you that this is the case. Okay, so what do I mean by jointly distributed random variables? It may be that we define multiple random variables on the same space. Okay? So it could be that I define one random variable, x, which counts the number of heads, and another kind of quirky random variable that's only binary. It gives you 0 if the first flip is tails, and it gives you 1 if the first flip is heads. So there's these 8 different sample points in the sample space, and these 2 different random variables map them to different real numbers. And so these are just, 2 variables defined on the same space. Okay? And you could define, of course, any number of such functions, an infinite number, an uncountably infinite number of such functions, because right, there's any infinite number of reals. Actually, I think it might even more be than uncountably infinite. It might be the next one up. What's it? Yeah, Beth 2 or whatever. Aleph 2. Yeah, it might be the next one up. I'm not sure. That's a Manuel question. And so here's one of those possibilities is x and another is z. Okay. So let's say x maps each to the number of heads in the sample, and z is the binary indicator for whether or not the first flip is heads. Some examples would be if I have tail, tail, tails. How many heads are there? 0. Is the first one heads? No. That's why there's 0 and 0. Okay, this one's 2 because there's 2 heads, and this is 1 because the first flip is heads. The joint distribution of 2 discrete random variables is just the collection of all possible pairs of a's and b's, where a is the range of the first random variable, and b is the range of the second random variable here. Okay? Or b are all the values in the range of the second random variable, I should say. So an example, if the first random variable I'm choosing is x, and the second is z, just adapting this generic notation, then I have the following distribution. There's 8 different possibilities, and here it is purely coincidental that it is the same size as the sample space. Right, just how many different combinations there are of a's and b's. And so if we look at what happens here, if we look at the probability that x is a and z is b, that's asking us, basically, out of those 8 sample points, how many of them have 0 as their, how many of them have, or rather, what is the chance that there are 0 heads and that the first flip is tails? So how many different sample points match this description? That was my speaker. Okay. Yeah. Oh, no. It's a head scratch. It says 8 different possible flips. How many of them have 0 tails? Or sorry, 0 heads, I should say. 0 heads. There's just one. It's the all tails. The chance of that is 1/8 because 1/8 of the sample points match these 2 random variables. Okay, how about this one? What's the probability that x1, or just x we can call it, is 0, and x2, or z, is 1? 0, right? Because there are no such inputs. Or there are no inputs to these functions. There's no sample point there. Because you can't have 0 heads and start with a head. Doesn't make sense. So that's an empty one. Okay. All right. Next one would be a quarter. And the reason it's 1/4, and you'll have another one in a second, but this one is, the probability is 1/4 because 1/4 of the different possible flips match this description. What's special about it? Well, we have 1 head, and we start with the tails. And hopefully you can convince yourself that's it. So my question for you, just to make sure this all truly, definitely makes sense, and your attention's not wandering, what's the other combination that has probability 1/4? And of course, feel free to chat. Okay, another like 12 seconds. Okay, so how else, or what else could it be 1/4? The answer, many of you, the most popular answer was indeed 2/1. There are 2 different ways that one can get 2 heads and start with the heads. So that's the other one that's 1/4. And that's the rest of the distribution. You can look at it for a second. Okay, so that's the joint distribution of these 2 random variables. Okay. Joint random variables also, just like regular old singletons, I'll call them, partition a sample space. So here are a bunch of different colors here. These bottom 2 colors are actually distinct. That's okay. The projector doesn't make that clear, sorry. So let's talk about those events. So the first event I have is the event where we have 0 heads and we start with the tails, and that's just that, right? It's this single outcome. These 2 right here are part of this event. This is the yellow event that looks the same color on the projector, is right here. Right here we have the green event, these 2 blues, and this purple. Okay, and if you can't see all these colors, it doesn't really much matter. The key point is that the original sample space is broken up into these 6 different events. Some of them have 1, some of them have 2 outcomes in them. Okay. Last lecture, someone asked about bijections, and the way I interpreted the question was, someone asked, is there a bijection? I was thinking, yes, there's a bijection between like which event you belong to and the number you map to, because it's one and the same thing, right? Like these are all the values that map to that value. So if you're wondering what I was thinking, that's why I was saying it. Yes, there is a bijection between basically your color and the value you map to, because they're the same thing. All right. Okay, warm up for the next thing we're going to do. Suppose we want to know, if we have this joint distribution, suppose we wanted to know the probability that x equals 1. In other words, the probability that the number of heads is 1. How would I compute that from the table below? What do you think? So I give you this table and I say, well, there's a chance you get, you're real lazy. What can you do? Yeah?
Where is a equal 1?
Yeah, here's where A is 1. So these two rows, and then?
You add the probability.
Yes, add the probabilities, because those are all the different ways that A could be 1. So we'll just add those together. So I get a quarter plus an eighth, and I get 3/8. Okay? That's called a marginal probability, and it's basically the idea is it's the probability of a single event. So in this case, x equals 1, without consideration of any related events. You compact them all to 1. Okay? Marginal probability, you can also form a marginal probability distribution instead of just get a single marginal probability as follows. So suppose I have the joint distribution, and now I just want to go down to just the heads and not care about the starting value anymore. Then I can just start adding up all the different possible combinations of B's that form each particular A. So first I'll add, for example, these top two rows. Okay, so these turn pink for a moment. 1/8 plus 0 is 1/8. Or we can form the union of these two sets to say precisely what is in that event. And in this case, I guess it's a marginal event. That's not a term we use in the notes, but it makes sense to me. Next is the one you just did. This one's 3/8, and then so forth. Okay. So this is a handy trick. We'll use it throughout discussions. There's not a lot of depth to it that I can bring to you in lecture, but we'll see it in discussions and homeworks. Yeah. How do we know there's no overlap? Because by definition, we're partitioning the sample space into these discrete events. Because when we originally formed these things, these are each functions. There's no possible way there could be overlap between these sets because these are different values. Like this is exactly the sample points which x maps to 3 and z maps to 1, which x maps to 3 and z maps to 0. And there's no way they can overlap, right? Because otherwise they wouldn't be distinct. Yeah, so once you say x is greater than or equal to 1, that's not, in this case, it's not going to, the joint distribution isn't expressed in terms of inequalities, if that makes sense. Yeah. So a joint distribution, distributions are always in terms of equalities, not inequalities. This is the boring version of that. Yeah. Okay? Because remember that an inequality, like probability of x is greater than or equal to 1, is now not just the probability of some events, but some combination of events, right? And so that's a different set of reasoning. Yeah. Okay, let's talk about independent random variables. Let's suppose we have two events in the same sample space. We're forgetting about random variables for a moment. We're going right back to our raw idea of having sample spaces and counting sets and that sort of thing. Like before we got to random variables, I want you to tell me, what does it mean for two events to be independent among these three choices? What applies? Okay, so if you need a concrete example to think about, here's some coin flips, whatever you want. So which of these three things would you select? Select all that apply. So I'll let you think about that for a minute, just to see if you remember what independence means. Okay, I'm going to wait for a juicy number of responses, yeah.
Earlier you said it's only going to be expressed in
Okay, I'm still waiting a little bit. I want you to form an opinion before I tell you what the answer is. Okay. All right, so this was just a definitional thing from a previous lecture. So the correct answer is only this second choice. For two events, the only thing you need it to be independent is that the probability of the intersection of the events is the product of the probabilities of the individual events. They can share outcomes, and let me give you a specific example. So I'm bringing this up because I know it's a common point of confusion what independence means. So let me give you two events that overlap, but are indeed independent. So imagine I flip 3 coins, as I've shown here. One particular event might be that the first flip is heads, and the second event is that the third flip is heads. If we look at what these events are, because an event is just a subset of the sample space, they overlap. There are some points in both sets, yet they are independent. Why are they independent? How do we define independence? What was the hallmark of independence? Well, it was simply that the probability of their intersection is the product of their individual probabilities. In this particular case, what's the probability of their intersection? 1/9. Okay, that's interesting. I don't know how that happened. That's funny. The probability of the intersection, I would call it a quarter and a half. There you go. Oh, it was thirds. Okay, if it was a third of the time, never mind. I tried to be clever, and I confused myself. I was assuming a fair coin, but me in the past was smarter. If the coin was unfair, if heads came up 33% of the time. Okay, it's a little richer. Thank you, Josh Huglast. You should have given me a hint, though, that this was an unfair coin. Okay. But if you want to make it fair, it's a quarter, a half, a half. Good. Okay. All right. So we can define independent random variables in a similar way to independent events. Now, independent events, I should note, here, let me give you the response. We were at about 40% of folks felt like there could be no overlap. So independence is still fuzzy for many of you. So it's a good thing to correct as you work through homework and discussion. But standing on that assumed foundation, which is not totally solid for everyone in the room, the idea is that 2 random variables will say that they're independent if the events p of x equals a and p of y equals b. These 2 events will say they're independent if for all values in the range that these probabilities, sorry, let me try again, that the probability, if we have x and y on this, that they're jointly distributed on the same space, that the probability that we get a and b at the same time is the same as the probability we get a for x times the probability we get b for y. Okay, it's very, very similar to what we were doing for coin flips, but this is a more generic framing that's going to work with us as we move through random variables. Okay. All right, so let me give you an example. Let's start with dice, which are very, very similar to events where we're just like almost feels exactly like counting. So let's say we're rolling 2 fair 6-sided dice. This time they're fair. Good. And let's say x is the result of the first roll and y is the result of the second roll. Very similar to coins. Well, these are independent because we have that for all of the a in the range of the random variable x and all of the b in the range of the random variable y. The probability that we get any particular combination is just the probability of the individual outcome, the probability of individual outcomes. Okay? So for example, the probability of getting, 3 on the first die and 5 on the second die is 1/36. The probability of getting just 3, if that's all you know, is a 6th. Probability of getting just, say, 5 is 1/6. Their product is 1/36. This is almost degenerate, maybe so trivial, it's not so enlightening. Okay? Another example, let's say rolling 2 dice. Okay? So let's suppose we roll 2 fair 6-sided dice where x is the result of the first roll and s is the sum of the 2 rolls. Are these independent? And if not, can you come up with some counter? And if it is indeed independent, give me an argument. So try and do this one. I'll let you think about this a bit more. Okay, I'll give you a minute or so on this one. I'll spoil the answer. This time we're at 85% of you felt like they are not independent, and that is indeed correct. And as an example, just as a quick counterexample, let's suppose we're considering the probability that the first die roll is 1 and their sum is 8. Okay? So what's the probability that happens? It's 0. Why? If you roll a 1, you can't get an 8. However, the probability x equals 1 is a sixth, and the probability that the sum is 8 is 5/36, which I just know from playing the game Settlers of Catan, but those don't multiply together to give you 0, so they're not independent. Any questions about that? So a natural question you might have is like, wait, didn't we already do all this a while ago? Like, why is this useful? You just made up a new thing called a random variable that like takes some of the samples and then assigns a number, okay? And now you're defining these events. Like x equals 1 is all of the die rolls that get mapped to x equals 1. Granted, right. For these simple examples, it's not necessarily super obvious why this is an advantage in terms of like being able to answer real-world problems. But random variables can have fairly interesting sample spaces, like a geometric random variable. It's actually an infinite sample space. It's the sequence of all flips of tails until you get a heads. Or a Poisson is even more crazy. Or later we'll talk about continuous random variables. So as we move, this is a slightly more abstract notion, is how I think about it, that is going to allow us to reason about more complicated randomness. More, we don't have to always be thinking about that underlying sample space like we are when we're thinking about coin flips and dice. This is another like higher layer of abstraction where now the sample space is infinite, or maybe just kind of abstract. We're not thinking about the sample space anymore, and it's more the random variable we're caring about, the distribution. Okay. And that'll become more clear as we talk about Poisson and especially continuous random variables. Okay, what about conditional probability? So this isn't even in the notes because it's considered so trivial that it's not in there. But the idea is that we could naturally write expressions like the probability of s equals 5 given that x1 equals 1. Okay, I want you to, in your mind, when you see x1 equal to 1, you're just thinking, okay, it's all the points that map to 1 under this random variable. And this is all the points that map to 5 under this other random variable. Once you think about it as just subsets of the sample space, there's nothing new here, right? The random variable is just a way to scoop up, because remember that these random variables are just partitioning the sample space. They're saying, nom, 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 you are in x equals 1. No, 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 no. These points are all in x equals 3. Right? They're just laying claim. They divide it into a bunch of different real numbers. And so this is nothing different than what you've seen before when you were doing just looking at the sample space in the raw. Okay? But if you wanted to, okay, so suppose we have these random variables x1 through x5 corresponding to coin flips, where xi is 1 if the ith flip is heads, and s is the number of heads, we could write something like, what's the probability that we have 5 heads given that the first thing is heads? Right? That's basically how you can think about this. And again, this is a very concrete example that we're comfortable with, but it'll hold even when the sample space is kind of fuzzy. And so again, what we'll end up with here, right, I've already just said that out loud. What we have here is that if our coin comes up with heads of probability p, then the probability that the sum is 5, if we already have 1 heads, will just be p to the 4th because we've already got one of them out of the way. Okay? We can also use the product rule with events defined in terms of random variables because, again, they're just events. So I could, for example, say, what's the probability that I get 5 heads and the first flip was heads? Well, that's just using the product rule, the probability that s equals 5, given that the first thing was heads, times the probability that x1 equals 1. And remember that this works even if the events are not independent. So that's a handy notion that we talked about. Remember the rocket being caught in the video. And so we can work out the math here, right? So the probability over here, just to show that it's true, the probability that you get s equals 5 and x1 equals 1 is p to the 5th, because you had to get 5 heads. The probability you get s equal to 5 if the first flip was heads is p to the 4th, and the probability that the first flip was 1 is p. And this will work always. Okay? So these last couple slides are review, but hopefully make things more concrete, that these are really just events. Though. If you just really trusted me the whole time that events are just collections of points in the sample space, then I wouldn't have had to say any of this. Okay? Lastly, we have mutual independence, which, actually, any questions? Okay. Last, we have mutual independence. So suppose we have, I don't know, 3 random variables. Very similar to before. We can define mutual independence in terms of events. I'm not going to read all this. I just want you to like absorb the, take in the vibes. And you can generalize this to any number of random variables. We'll talk about this sort of thing a little later, but just want to acknowledge that, yes, there is also a notion of mutual independence for random variables. Okay. A really common idea, and one that we're going to use today when we do some expectation magic in a bit, is this notion of independent and identically distributed random variables, also called IID. And here independent it means mutually independent. And the basic idea, imagine, for example, that we roll some die of some number of sides 13 times. Then we would say the resulting variables x1 through x13 are independent, because each roll doesn't affect the other, and they're identically distributed, because they're all die rolls, right? Or, as a more practical example, let's say I'm in a factory, and I want to know, I don't know, I mean, how strong are my boxes? I need to make a claim to sell my boxes wherever boxes are sold. Anybody expert on cardboard boxes, by any chance? No? Oh, yes? Okay. One day I want someone to be good at them. Because there are people who are very good at boxes, of course, and everything else. But we want to test crush strength. So we could say that the resulting observations are IID, right? And there's this mapping that we'll talk about a little later between the real world and these random variables, because random variables are a model for the world. Actually, at the end of the lecture today, we'll see such an example. And so you can think about your crush strength modification, or crush strength tests as IID. Okay. All right. Oh, wow. You're doing good. Okay. That's vignette 2. So we've talked about jointly distributed random variables. The basic idea, if you have multiple random variables on the same sample space, they partition into all possible combinations that those 2 random variables map to, right? This third vignette is going to be about the linearity of expectation. This is such an incredibly useful and important technique. I think if you had to pay attention or just ingest one part of this lecture that's super, super important, it's this one, because it's such a handy idea. I want to give you an example of why this trick is so useful. First, let's say that S is the sum of rolling 2 6-sided dice. So we might ask ourselves, what is the expectation of S? Last time, I mentioned what this distribution looks like. And if we wanted to, we could compute the dot product of these 2 different columns. The dot product is just this times this, plus this times this, plus this times this, all the way down. And that would give me the expectation, which is 7. Okay? This is pretty annoying to do, but you can. What the linearity of expectation lets you do is it lets you avoid having to do this huge computation. Okay? So the punchline, and I'll prove it in a moment, but the punchline is that for any 2 random variables, x and y, as long as the expectations exist, not on the slide, but as long as they exist, the expectation of x plus y is equal to the expectation of x plus the expectation of y. Okay? And that's true no matter what these random variables are. They could have any degree of dependence. They could be the same distribution. They could be totally different distributions. But you get the expectations just sum, okay? And I'll prove it in a moment. But this is true for any 2 random variables, no matter what. Okay? So let's consider dice as an example. So if S equals x plus y, then the expectation of S is going to be the expectation of x plus y. If I just apply this property, I can say the expectation of x plus the expectation of y. So what's the expectation of a single die? Well, I mean, that's still a little annoying. I got to sum 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6 and get 3.5. That's not so bad. But then once I have 2 dice, then I get to say it's times 2. Right, there's 2 dice, so the expectation's twice as big. Maybe that's not so surprising, right? Like if I roll 5 dice, the average number I get is going to be 5 times as much as I roll 1 die. But we'll see that this is an incredibly powerful technique, even for pretty tricky problems. We'll have a couple of really good ones. Okay, so I'll set this one aside for a moment. So first I want to prove to you that this is true. Now I know some of you aren't happy with just one formula for expectation. You're not happy with just 2 formulas for expectation. Maybe you want a third. Who wants a third? Yeah, right. You're feeling me, right? We need more, okay? What am I going to do? Here's our usual expectation formula. I'm going to give you the following, okay? So this new formula, which I will show on the bottom first, I call this the mega verbose formula for expectation. Okay, like what? What is this? Okay. let me tell you why this is the same as what's up at the top. And why am I showing you this? This is going to make proving linearity of expectation easier. And secretly, we've been kind of using it. Okay? So up top, we know the following. We know that the probability that x equals a, this is the probability of some event. Which samples are in that event? I asked that question much earlier in lecture. It's all of the samples that we put them in x. X goes, and whichever ones go to a, however many of those are, if it's a uniform probability space, you sum up the size of that set, divide by the total size of the sample space, and you get the probability, right? So in other words, it's just the sum of the probability of the individual events. So if they have different probabilities, right? Sometimes you have weighted dice or whatever. We're just summing up all of the omega in that set. You could put parentheses around this if you want. I'm not going to, but omega, there's a bunch of events that are all the ones which x maps to a. Okay? And we're just going to add up their probabilities. Okay? Now, since x is a function, each outcome is going to belong to exactly one event. We don't need to worry about, as someone was mentioning earlier, we don't need to worry that somehow multiple outcomes end up in the same event. That's not allowed because it's a partition. So let me give you a little example here for 2 dice. To make this really clear based on an example, what are all the combinations of 2 dice? So we have 1, 1, we have 1, 2, we have 1, 3, we have 1, 4, and so forth. So what's the expectation? Well, I can just take that and say, for every single possible thing that can happen in my sample space, you take that and you multiply by its probability. And you do it for every single individual sample. Okay? Before our expectation formula, it wasn't as verbose. It took all the things that map to the same value and it put them together. Because you don't want to count all 36 of them. That's a little annoying. With the original version, we were summing up all of the things that all map together. Like the event was handled all at once. Now we're just basically making a lot of copies of the same thing. All of the ones that are, like say there's 32 different things in some particular event. There's going to be 32 terms here instead of just one. Does it make sense? Maybe? Questions about this formula? Okay, so this is going to make our life more convenient for this proof. I think the words I said are a concise way of putting it. Reaching your soul might be hard with this one. Yeah? Say again? Oh, what does it actually go to? Right. Let's see. S of, yeah, this is 12, right? Yep. It would be 12 indeed. And that makes sense because it's like 12 happens, or this particular 12 happens 1/36 of the time. That's the way to think about it, right? There's only one, this is actually, there's only one 12, of course, right? 6 and 6. This one, for example, there's 1 and 2. S of 1 and 2 is 3. And what you'll end up with here is you'll have, how many times do you get 1, 2? Like 1, then 2. Question for you. Let's have a little conversation and you can all listen. How many times do you get 1, then 2? Once, right? But how many different times do you get 3? 2. You could have 1, 2, or 2, 1. So in the normal expectation formula, they're lumped together. It's 2 times, it's going to be 2 times, or basically those 2 are all together, right? Here, there's 2 copies. Okay. Yeah?
So the random variable mapping for like the pair is the sum of the 2.
Right. This particular case, this random variable S maps the sum into the sum. Yep.
But then there would be like, as you just said, like S of 1 and 2 and S of 2 and 1
Mm-hmm.
would both be 3.
Right. Exactly. Yep.
It would be like duplicate.
So yes, because there's 2 different ways it can happen. Right. There's 2 different ways to get 3, and that's how you get that weight into the sum.
But then, doesn't that violate bijection? Because like, if you have 3, you don't know if it's 1 or 2 or 2 or. I don't see what you mean. Say again. Like, a random variable is a bijection, right? So that would.
No, a random variable is the bijection thing I said before was talking about. There's a bijection between which event you're part of, what value you map to, because those are the same thing. But in general, you can't go back, right? Because there's many different ways to get there. Yeah, that was the thing I misspoke because I misunderstood what someone had said. Right. Okay. So hopefully this makes sense. It might be a little fuzzy, but if you trust me, so if you still don't totally buy this, trust me that top formula is true. And if we get through this derivation, you don't totally have it, please revisit it. But what I really want you to understand is how it's so useful, and then offline you can digest it further if necessary. So using this mega-verbose form of the expectation, we can say that, suppose we have s equals x plus y. Well, we can write the expectation of this sum as follows. We can say the expectation of x plus y is the expectation of s. The expectation of s is just this mapping, like for every one of these different pairings. So there's 36 different terms in the rolling 2 dice example. So in that case, the size of this sample space is 36. We're going to sum over all of them, okay? Well, since s of omega is just the sum of x of omega plus y of omega, because how does it work? I mean, it takes the first value and it's just it basically says, I guess it's an identity function that just says if it's 3, it's 3. And for the dice example, and the other one the same. So it is that sum. I mean, it says so right here too. So we keep going. Now, what's nice about this is that we can just say, okay, well, if I'm doing x of omega times x of omega plus y of omega, which is just some number, times p of omega, we could just break that into 2 copies, right? I could just say, let's take the x of omega and the p of omega and put them together, the y of omega and the p of omega and put them together, and I could have kept it in one sum, but I broke it into 2. Why not? And at that point, then I'm just there because that's the mega-verbose form of the expectation for x and y. If it doesn't make sense, I would encourage you to just take some small toy example of a random variable, like, I don't know, say rolling 2 3-sided dice. And if you write it out, the expectation in the mega-verbose form, you'll just be like, okay, that'll make sense. All right, I don't want to belabor this because it's like one of those things that's almost so simple it's confusing. The classic example, this is not this simple, but I remember in high school calculus, we had this math problem that was, what's the limit of 4 as x goes into infinity? I was just like, what the hell? You can't do that, but you can. It's just 4. Okay, so it's not that simple, but it's in that direction of like something almost kind of obvious where it's confusing. Okay. We can also show that there's another piece of the puzzle, which is that if I take a random variable and I just multiply it by c, then the expectation of c, where c is a scalar constant, then we'll get c times e of x. That's an exercise in the notes, so I'll leave it that way. And when we say that expectation is linear, or that we have linearity of expectation, we're saying that these 2 properties are true. That we can sum the expectation of 2 random variables to form the expectation of their sum, and also that we can scale up a sum. Okay? You can also combine these into a single statement, which is that the expectation of a scaled sum of 2 random variables is a times e of x plus b times e of y. I'm not going to say much about that. Okay? So I want to note, though, derivation aside, I'm happy with the derivation, but I know that it's probably didn't sink in for lots of you. What I really want you to know is that expectation is linear. I know it says expectation and linear. Expectation is linear. We're going to fix this one. Even if x and y are not independent. They could be anything. So just to show you just how powerful this idea is, let's talk about, for example, a binomial random variable. Okay, so the binomial random variable is we're flipping in coins. They each have a probability of heads p. Okay, we could say, what's the probability I have some specific number of heads? Well, it's in choose I because that's the position of the heads. We do p to the I because we do p to the I times 1 minus p to the n minus I because that's the probability of any specific examples where we have I heads. And if we wanted to find the expectation, we could use the usual expectation formula. We could sum this up. We could say, okay, it's that formula times I. We take I equals 0 to n. And you could do a bunch of algebra and get an answer. And it will be the right answer. But it will be a lot more complicated than simply using the linearity of expectation. Okay? This is very tedious. So what we can do instead is just say, well, what is a binomial? It's just the sum of Bernoulli's. It's the sum of coin flips, right? Like, I flip 8 coins. That's a binomial with n equals 8 with that same p. It's the same exact thing. If that is the case, then we just need to know the expectation of a binomial, or a Bernoulli. And the expectation of a Bernoulli is just p, which we showed in the previous lecture. Okay? So we have that the expectation of x, if it's just the sum of all these different Bernoullis, it's going to be the sum of the expectations of n Bernoullis, which is just going to be np, which is extremely easy compared to, imagine trying to, on an exam, for example, form that sum. Like find the closed form solution for that sum. Wouldn't be that fun. It's NP. And this is an argument for it that is much simpler than a bunch of algebra gymnastics. Any questions about this? Okay. But you might say, aren't those independent? Like, I'm not that impressed. Like, yeah, this is back to like, sure. You flip 37 coins and you get 37 times as many heads. Like, you've proven something that's obvious to me, even if I'm sleepy right now. Okay, well, here's a harder one. We have this distribution that we derived from scratch that was a little ugly. I have 3 students. You give me all your homework. I give them back randomly. What's the chance that none of you get your homework back? Well, it was 0.3, whatever that is. 1 is a half, and 3 is the least likely thing that actually can happen. And you can never have 2, because I can never get 2 of you get your homework back and 1 of you doesn't. Doesn't make logical sense. So that's why this one's 0. And we worked that out before. Okay. So let's suppose I wanted to know if I took everybody in this room, all 100-ish of you, and I took your homeworks and I shuffled them and then I gave them back. On average, how many would you expect to get back? And you might think it's like, I don't know, maybe it's like the birthday paradox and it's like square root or something. Or maybe it's like 6. I don't know. You could try to form this expectation by computing each of these individual probabilities, right? Oh, and this is not a factorial. This is a excitement, okay, to be clear. So the probability that x equals 0 is some number which you can compute. You have to count the number of possible derangements, which we did not do. Specifically, we skipped it, but it was in an earlier notes as an optional topic. Probability that x equals 1, x equals 100, and then up to n, whatever n is. And then you would add it all up. And it would be, again, a bunch of algebra gymnastics. But we're only doing one algebra gymnastics today, and it's not this one. Okay? So here's what's really cool. And this is a very common and very cool trick. Okay? I'm going to do it much better than computing the individual probabilities. What I'm going to do is this very clever idea is I'm going to create x as the sum of many different random variables. Okay? So it seems a little weird. I just showed it on the screen. But like, how would I form this as a sum of random variables? Any ideas? Somebody who didn't just read it or has not seen this before? Any sense? What's the biggest it could be? So if there's 130 people, what could x possibly be? 130. Smallest it could be is 0. Okay, so let's try and think about it. Like, how many random variables might I sum up to get the total? N, yeah. Okay, and what would each one mean? Whether the ith student got it back. So did you get your homework back? Did you, and so forth. So we have n different random variables, which is did you personally get your homework back? That's the idea. Okay? So we'll define a random variable, which is 1 if you get your own homework, and 0 otherwise. Question, are these independent or dependent? What do you think? I didn't ask on the slide, but what do you think? Dependent. Why?
Because if you have, you can't have n minus 1 students get back their homework and 1 student not get.
Right, yes. We have a counterexample, which is that if students 1 through n minus 1 get their own homework, n also gets their homework. You can't be the only person that didn't get your homework back. That's impossible. So there's dependence between them. Despite the fact that I don't really know how those things interact. It's like a big, complicated, messy thing. Even though I have no idea what this distribution looks like, and even though I don't know anything about the dependencies between these different indicators, I can nonetheless use this to compute the average number of homeworks that get passed back. Okay? So, what is it? Try and think about this. Okay? I'm going to let you solve this one. You get a minute and a half. If you fell asleep, come back. That wasn't a call out. So I'm going to rephrase it if you're kind of confused about where to start. If I take everybody's homework and I shuffle them, I give you back your homework, what's the chance you get yours back? If there's 100 students, let's say. That's the first question. Okay. So the chance you get your homework back if there's 100 students is 1 out of 100, or 1 over n in general. And then if there's n of them, right, you're just going to take 1 over n. So first of all, I should say the expectation of any of these individual indicator variables is 1 over n. It's a chance you get back your homework. And if I just multiply that by n, I get 1, which is kind of surprising. If I take 100,000 people and I shuffle all their homework and I give them back randomly, 1 person on average will get theirs back. There's a LinkedIn post I'll have to show you later. I'll save it for next time. It'll be, I was a smart ass on LinkedIn one time, if you can believe it. And I'll share that story later that relates to this distribution. Okay. All right, any questions about this? So what I love about this, what's profound about it if you zone out a little bit, is that these eyes have some weird dependency between them that's kind of hard to put your finger on, but we do not care. And because we don't care, we can get an answer to this nice problem without doing a ton of work. Yeah? So the question was basically, are there, in a probability question on a final, is it possible that you have a random variable that you need to decompose? Sure, that seems like a good trick. I mean, one of the tricky things about teaching a math class, of course, is that, I mean, people describe mathematics as like chess against God, and you need to give sort of like small enough puzzles someone can do it. So, I mean, if there's an interesting puzzle that's the right size, then sure. But yeah, what we strive to do, though, is that the discussions and the homeworks are somewhat more difficult than the exam problems, and then you get a sense for what techniques are in scope. But, you know, it's math, so it's a giant universe, what can happen. And Manuel's a lot better at it than me. I'm getting good, slowly. All right. Okay, one more little topic of the day. So we're going to use what we've covered today so far and talk more about Poisson random variables. Now, I should note that if I had thought carefully ahead last year, I would have done Poisson later, and we would have started with Poisson now instead of having it as like this thing you see and kind of half understand in the first lecture. For various reasons, I didn't do that. I inherited some structure, sorry, but so it goes. So I'm going to wrap up today by going to Poisson Village, and we're going, town, I guess, sorry, it's upgraded. We're going to use today's new material to derive where a Poisson comes from, and then if we have time, we're going to show that the sum of 2 independent Poisson random variables is also Poisson. So what is the Poisson random variable? First, I'm going to tell you what it was just at that base level we had before. It was kind of like very different than our other random variables. Like, I guess it made some sense. It's like a thing you can, like a function you can call in a programming language. Like, you have no idea where it came from, but I told you the following. If you have a random variable with expected value lambda, the probability that x equals I is that, right? So for example, if we have a radiation source that emits 4 alpha particles per minute on average, I should say, on average, then the probability that we get 0 emissions, taking that example that someone asked about during lecture, would be 4 to the 0 over 0 factorial times e to the minus 4, which is 1.83%. But like, what is this formula? Where did this come from? It was just given to you for no reason. So I'm going to justify this formula. There's 2 parts to the story. The first part's pretty interesting, which is the part where we derive the formula. And then there's a boring part at the end of lecture where I'm going to do algebra gymnastics, and it'll probably be a waste of time, but I will put it down on a video so you can look at it later. But it'll be the end of a long lecture. Sorry. But the part I really want you to get is to understand why we start doing the ugly algebra sum in a little while. Okay. So unlike our other random variables, we never really talked about where this expression came from. Bernoulli was trivial. Binomial took some exercise with our counting lectures. Geometric also was just like, we derived it from first principles without too much work. Poisson's a lot more work to talk about where this comes from. We're going to derive it from an infinite series of coin flips ultimately. Okay, so why is that going to happen? I am going to note that we're going to use this random math fact that the limit then goes to infinity of 1 minus x over n to the n is e to the minus x. I'm not going to prove it, sorry. You can, I mean, if you remember the formula for E, which is 1 plus 1 over n to the n, you get E. Maybe it's kind of plausible that that's the case. It's not too hard, but there's already too much algebra in the lecture. So this is just a fact from the universal trust. We're going to use that later, just a note. And we'll get there in a bit. Okay. So as a thought experiment, imagine you're running a rural telephone network. Why rural? Because not too many phone calls are made. Okay? And we want to model how many phone calls do we get a minute? Why might that be useful? Well, why might that be useful? What do you think? Yeah?
Say we want to know how much electricity we're going to actually end up using.
Sure, we can model how much electricity we're going to use. We might also want to discover what else? I don't know, something else might be useful. Yeah? Oh, no, here you go. Oh, nope, busted. Go ahead. Yeah, how many operators can we hire? We're going old school with the that's fun. Yeah, how many operators need to hire so we can handle max demand if it's an old school, plain old telephone system where we need operators. Let's say we know that we get 4 phone calls per minute because that's some data analysis that we know from a similar town. And we want to know, is it ever going to be the case we're going to get 30 phone calls? Okay. Well, one way we could try to model it, and this is a very crude model of human behavior and does not take into account important things like people don't make phone calls at 2 in the morning. But let's say that we're going to be very crude. Our first order model is going to be that it's a binomial random variable. It's kind of how I'm going to think about it. I'm going to write a little simulator. And I'm just going to divide. My goal is to figure out the number of calls per minute, let's say. And what I'm going to do is I'm going to divide each minute into n slices. So maybe I pick n equals 60. Then each slice is going to be 1 second. And then we're going to flip a coin. And every time it comes up heads, that means a call was made. And if tails, no call was made in that slice. And what's p here? Well, we've got to figure that out. We want to pick a p such that we match that 4 phone call average. Okay? Now, you might say, if I already know it's 4 phone calls on average, what am I even doing? Well, what I'm trying to do is not just get the average, but also estimate the probability that there are no calls, that there's 30 calls, that there's 12 calls, just from that average. Okay? And I'm making big assumptions here, namely that this coin flip is a good model of human behavior. And again, this does not take into account there may be a fire. This does not take into account, Packers won the Super Bowl. Whatever it might be, this is not, we're not doing that. We're just saying people flip coins. They randomly make phone calls. If that's our model, what happens? Okay. So let's suppose I pick 60 as my number of slices. So my minute gets divided into these 60 seconds. And we've done that. This right here, if a call gets initiated at, say, times 3.3 seconds, 10.5 seconds, 14.2, 30.1, 38.9, and 48.3, then I have these 6 heads. So I got a heads here. I got a heads here and so forth. Okay? This specific outcome that I show here is one of 60 choose 6 that comprise the event x equals 6. So any combination of 6 blue bars will count. I don't really care about exactly how many of them right now, but that's the idea. It's a crude model of how you might simulate human phone calls. And if that's your model, you can start to ask yourself questions. Before we get to answering questions, I want to think about, if this is our model, what are the n and p's, as we're trying to be data scientists or I guess phone network engineers. If we're calling this a binomial, what's n and what's p? So we'll start with n. So if this is my setup, what's n going to be? This is a are you awake type question. The next one's a little harder. Uh-oh, it's the same question again, isn't it? Is it showing up wrong? Oh, it's the wrong QR code. That's interesting. Let's fix it. I guess. I think it's worth it. If you ever want to make a QR code, please go to joshug.ug/qr.html. You can make your own QR code, but with no white space around it. Okay. All right. Maybe that one will work. But if it doesn't, I apologize. Okay, let's try again. Those QR codes are free, by the way. You do not have to pay me for these QR codes. This is science. Okay, now let's see if this will work, though, because I'm a little nervous about something. Okay, what's in? Yeah, All right. Okay. All right. So I think folks who are saying number of calls is fine. Most of you said 60, which is what I had in mind at least. Next question is, what's P? So if I want to match this, if the goal is to make this mathematical model match what I'm deciding, what's P going to be? Think about this. This one I'll give you slightly more time. Remember, P is the probability that any flip comes up heads. Another hint, I did this after I talked about the expectation of a binomial. I'm going to sit in the chilling chair. What do you guys think? Okay. Quick interlude. What's the expectation of X? X is the number of phone calls per minute. What's the expectation of X? What should it be? 4. Okay. So if the expectation of X is 4, then what? Keep thinking. Okay, I'm going to give it away. So if the expectation of X is 4, so the expectation of X is 4, and we know the expectation of a binomial random variable, which we've all memorized, perhaps, is NP. What's n at 60? So if 60p equals 4, p must be 4/60ths. Okay. So not so crazy, but that's the idea. If I want to simulate human behavior as making phone calls, where there's 60 phone call kind of chances, 60 seconds per minute, then the probability any particular person makes a phone call is 4/60ths. Okay? So using this, we can now, this is a model for how the phone system's going to work. If I want to know what's the probability that X equals 0, I can use this distribution for the binomial. So I guess first of all, when I say probability X equals 0, what does that mean? I just said it out loud, but it tells you what? The chance that what? That there were no phone calls. And how do we compute it? You plug it into the binomial formula, or you just remember, I mean, you can also just think of it, it's getting 60 tails in a row. So it's going to be 1 minus p to the n. 1 minus p is 56/60ths, n is 60, or 1.6%. So this model suggests if you have 4 phone calls per minute on average, and you model, then that's a choice. Your model might be wrong, but if you make the choice that it's 60 independent phone call decisions, like, should I make a call? Nah. Should I make a call? No, I'm not doing it. Then the chance will be 1.6% that nobody makes a call. Okay? All right. Let's talk about a limitation of this model. And this is probably the most interesting question in today's lecture. Why might a binomial random variable be kind of subpar in some way? What can happen in the real world that could never happen in our model? Okay, so try and think about this. I'll give you, again, a minute or so while I sit in the chilling chair. Feel free to talk to your friends. And it's not something like the phone network is on fire, right? That's not what I'm going for. I want something more essential to the problem. I'll write some, well, maybe I'll write some interesting answers. I'm not going to write. Okay, I'll take some thoughts out loud. So give me one thing that doesn't map, yeah? Or actually, I'll go here first, yeah? 2 calls in the same interval. That's one problem, and that's the one we're going to fix. Other problems, though. How does this not match reality? Yeah?
People don't necessarily call volume is not necessarily uniform.
Right, we don't expect P to just be some constant forever. Yeah, exactly. We can't fix that one with what we're doing today. You could in some other way, but we're not going to. Any other thoughts? Yeah. Yeah, more than 60 calls a minute is another way of putting it, right? That's a pigeonhole principle version of the same argument someone else made. What if you get 2 calls in the same interval? Or, equivalently, there's no way you could get more than 60 calls in a minute here, which could happen. So how do we fix that? What should we do to fix the no 2 calls in the same interval problem? No, I'm going to take someone else. Yes. Yeah, pick a smaller time interval. So I'll just shorten the time interval, whatever that might be. Okay, so instead of doing 60 intervals, I'll do, 60 million or something. This one is not a submission question, but let's think about it. Okay, so earlier we said if we did 60 time slices and lambda was 4 calls per minute, then the model was binomial with n equals 60, p equals 4/60. If we now go to n slices, which one do we get? Let's get a show. Let's get applause. That one. Okay, that one. That one. That one. Tepid applause for that one. Okay, yeah. Looks good to me, I think. Okay, good. So that's the one we're going to use. We could just pick more. So we could say, 60 million. So every microsecond. Okay, well then we just do the same thing. Now the probability is 4 out of 60 million microseconds. So now you're sitting there in bed thinking like, call, you're like just like vibrating in bed. Saying no most of the time. Okay. In that case, if we want to know the chance that there's x equals 0 calls, then we'll do the same thing. What's the chance we get 60 million coin flips, which are very unlikely to be heads, and we get 1.83%. Okay? It's different than what we had before. Before it was 1.6%. This time we got 1.83%. And if you were paying super close attention, you might recall that when I did a Poisson random variable, we also got around 1.83%. So by increasing the temporal resolution of my experiment, what I'm doing is I'm moving towards a Poisson distribution. Quick question. Do you know where E came from, the number? Compound interest. Very similar argument here. With compound interest, the question was, okay, we could compound yearly my interest. Well, what about monthly, daily, versus continuous? This is the same thing. That's why E also pops up here. This is the infinite number. If you have a continuous number of experiments, you will converge to a Poisson distribution. This is pretty close to where we're going to go. Okay? All right, so this is more accurate. And why? Just to go back to this. We already said this, but if you use microsecond time slices, I say the 1.83% number is more accurate. That is, if you gather real experimental data, I think it'll tend to be better. Again, I'm ignoring that humans don't just decide randomly and make phone calls, but hey. But if we were doing like alpha particle emissions, this will work pretty well. So why? Why is it more accurate fundamentally? We fixed one problem, which was we reduced the likelihood that we have 2 calls at once, 2 emission events at once, whatever it may be. That's all. Okay? All right. We could use this formula if we wanted to compute other things, like what's the probability of x equals 17? Well, there's 60 million choose 17 different ways to get heads at all those different microseconds. Okay, what's the probability of any such outcome? It's this big expression, assuming there's no typos, but I think it's right. This is an awkward computation, but the good news is, first of all, as n gets bigger, this gets more accurate. And the other thing is, in the very large n limit, this expression actually gets easier. Sometimes that happens. You pick such a big n, then you don't have to do all this crazy choose madness. You can go to algebra hell for just one moment, do the algebra hell one time, and you're happy. So in these remaining 8 minutes, let's do a lot of tedious algebra. and then we'll call it a day and have the rest of our Tuesday to ourselves. Okay, so I hope you will agree with the first line, and then the rest is the story of algebra. If we have a binomial random variable where we do n flips and it's lambda over n p, then the probability that x equals I is going to be there's n choose I ways to get that specific number of heads. And then the chance of that specific outcome is going to be the chance of heads to the I times the chance of tails to the n minus I. Okay, I'm going to expand out here first the choose function, right? That's all I've done here. I don't usually do that, but I'm going to do it because as I take the large n limit, I'm going to be able to cluster terms and make things disappear. Okay, so what I'm going to do here is I'm going to take that expression and I'm going to make it into 4 pieces, each with a slightly different color. The colors aren't super important, but if you can see color, I guess it makes things a little nicer. First, I'm going to collect these red terms, which is this lambda in the middle expression to the I. Okay, so the lambda, the I are red, and this I factorial is red. You bring these over to the side, and I get lambda to the I over I factorial. Okay, and this arrangement of terms I'm going to do here is arbitrary, but the rough goal, the reason I'm doing it, is I want to cluster things together so that when n is large, they go away. Now, in this particular case, these are the constant terms that have nothing to do with I, which is why I put them there. Okay, that's the red terms. Next, I have the blue terms. So what are the blue terms? They're n factorial over n minus I factorial, and then this n to the I. We've already pulled out this lambda to the I. Okay, and again, I'm just pointing this out if you cannot see colors. And then right here, this is what happens once you pull all that out. I got n factorial over n minus I to the I factorial times 1 over n to the I. This is just n to the 1 over n to the I. I've written it slightly differently. That's the blue terms. Next, I have the gold terms, which is most of this expression. That's 1 minus lambda over n to the 1 minus lambda over n to the n. Okay, so I'm not doing that part. Okay, that's the gold part. And then lastly, I have the purple part. Okay, I just basically broke this into 2 copies, one that's to the n and one that's to the minus I. Okay. To get the Poisson expression, I'm going to take each of these things and take the limit as n goes to infinity. The limit as n goes to infinity of this is that calculus problem I had in high school. Nothing happens. This one is going to turn into 1. This one's going to turn into something nice. This is also going to turn into 1. The blue one's the annoying one. Okay. So let's talk about the limit of the blue sub-expression as n goes to infinity. What's this thing? All right. I hate this, but you're in this boat with me. So let's go. So this expression right here, which I've just copied and pasted down here, I could expand it out like so. I'm just keeping the 1 over n to the I right here. I'm keeping this as n minus I factorial, and then up here I'm just multiplying out this n factorial, and I am left with this. Right. That looks weird though. Is that wrong? Or is it right?
I don't think there should be an exclamation mark.
Is it right? Hold on. N? See this? All right, told you it was algebra hell. Expand. N times n minus 1 times n minus I plus 1 times... Oh, right. Yeah. This is the rest of the terms. I've left them unexpanded. Good. Right. Thank you. Neat. Okay. As someone just noted, I can then cancel out these last so many terms, right? So I'm going to take these terms and cancel them out. Good. Okay, so I've gotten rid of some stuff. Not totally done yet. But here, I now have a bunch of n's minus something. Okay? But they're basically n's. So I have n over n times n minus 1 over n times ... times n minus I plus 1 over n. Okay? As n gets really, 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 really big, this thing's just going to be 1 because these are all just like, it's like 1 times a number slightly less than 1 and so forth. So as n gets really big, it'll go to 1. If you really want, you can write it out as follows here, where like maybe I pick I equals 4 and n equals 10. Okay, maybe that'll help convince you. What really happens over here? It's 10 factorial over 6 factorial times 1 over 10 to the 4th. That's what's over here. If I expand that out, it's 10 times 9 times 8 times 7 over 10 to the 4th. Okay? Which is just simply, if we like break it into individual terms, this is just giving you a number. I should note, by the way, when I take math classes, I don't think it's very common for instructors to do this. Like, there's the formula, here's a little example. I don't know. It's something about the way my brain works. I want to see a concrete example to be fully convinced. So it ends up being 10 over 10 times 9 over 10 times 8 over 10 times 7 over 10. And if we bring up n really, really big, it makes sense that we should end up at 1. Okay? a little fuzzy of an argument, but hopefully convincing. Okay, that's the hard one. Okay, what about the limit of the gold? Well, that one I punted, and I said, hey, we're going to use this this fact that this is just going to be that the limit as n goes to infinity of 1 minus lambda over n to the n is going to be e to whatever's up here, okay? Or e to the minus whatever's up there. Okay, so I'm just giving that one for free. Okay, you could prove it if you want. I'm not going to. So the first one we got 1. The second one we got e to the minus lambda. And then we have one more to go, which is the purple expression. Oops. So the purple expression, this one's relatively straightforward. If we bring up n really big here, that n's going to swamp out this lambda. We'll end up with 1 minus 0 to the minus I. Doesn't matter what I is, we end up with 1. Okay? So the punchline is that the limit of the blue expression is 1. The limit of the gold expression is e to the minus lambda because of that formula I said I'm not going to prove. And lastly, we have the limit of the purple is 1. So we're left with simply that the overall probability, once you go to the large n limit, is just this lambda I to the I factorial that we pulled up. And then this part, which is the e to the minus lambda. And that's where the connection to this like continuous compounding comes in. We did an infinite number of experiments. That's why e is popping up there. Okay? All right. So that leaves us with this Poisson random variable. So if we were to take that formula and then we try to plug in the probability that we have x equals 17 calls in a particular minute, then we just have 4 to the 17th over 17 factorial times e to the minus 4. Okay? All right. And these two values are close if you compute them. I'm not going to do it, but you can show that they're both around 1.83%. So to summarize this little distribution, the Poisson random variable tells you the number of events that occur in some fixed duration time interval. I picked a minute. It could be an hour, whatever. But the key thing is that whatever your units of lambda are, that's what your Poisson's telling you. When you have the probability that you have a specific number of events per unit time for that random variable. So the critical assumptions to be Poisson are, first, you have to know that, you have to know the following. You have to know that the time intervals are independent. An example of something where that's not the case is like a rapidly decaying radiation source. In that case, knowing how many events there are early will tell you that it's going to be less radioactive later. So knowing about one time interval doesn't tell you about the others. And you have to say that the number of events that occur are some average constant lambda. And the specific modeling choice that gave us the Poisson distribution is to think about it as a binomial random variable over very short time intervals. Okay? And the last thing I'm going to do, and I didn't think I was going to get here, but there are slides that cover the sum of two Poisson random variables. This is primarily an exercise in algebra, and I think you've had enough. So I will just flash them through so that they're on the video, but they are in the notes. Okay, thank you, everybody. Hope that was good. See you Thursday.